Welcome to Get Your FRQ On. This question is from 2019. It's question 4, and it is not calculator active. In the question stem, we have a rain barrel, which is collecting rainwater, and we have a differential equation representing the height of the water in the barrel at time t. So we have dH dt and a cylindrical barrel. In part A of the question, we are asked to find dV dt when the height is 4 feet and to provide the units. All right, since the barrel is a cylinder, we know that the volume of the cylinder is pi r squared times h. Using implicit differentiation here, dV dt is pi times 2r dr dt times h plus r squared dH dt. However, the radius of this rain barrel is 1, and the radius never changes, so dr dt is just 0. So using that information, we can simplify our expression for dV dt to just be pi times dH dt. All right, when the height is 4, dV dt simply requires that I plug in 4 for dH dt, and then I get pi times negative 1/10 times the square root of 4, which is negative pi over 5. So when the height is 4 feet, the volume of water in the rain barrel is decreasing at a rate of pi over 5 cubic feet per second. In part B of the question, when h is 3, is dH dt increasing or decreasing? And provide your reasoning. All right, so dH dt being increasing or decreasing would be something we would need the second derivative for, so we're going to find d squared h dt squared. And after finding the derivative of dH dt, we get what amounts to positive 1 over 200. And notice that that is constant. Right? At 3, when h is 3, the square root of 3's cancel out, as they would for any value of h. We just get positive 1 over 200, but what's important here is that we get a positive number. So at h equals 3, or when the height of the water in the rain barrel is 3, dH dt is increasing because 1 over 200 is positive. In part C of the question, when t is equal to 0, h is equal to 5, and then use separation of variables to find h in terms of t. Okay, so we take our differential equation, dH dt equals negative 1/10 the square root of h, and we separate. We get dH over the square root of h equals negative 1/10 dt, and then integrate both sides. After integrating both sides, we get 2 times the square root of h equals negative 1/10 t plus a constant. Using the initial condition that when t is equal to 0, the height of the water is 5, we get 2 times the square root of 5 is negative 1/10 times 0 plus the constant. This implies that the constant c is 2 times the square root of 5. Now that we know c, we can plug that back into our general solution and finish solving for h. 2 square root h equals negative 1/10 t plus 2 square root 5. If I divide everything on the right by 2 and then square it, I get h equals negative 1/20 t plus a square root of 5. And then I have to square that, and that is h in terms of t.